Hello and welcome to today's lecture on supply voltage scaling. This is the second lecture on this topic. In the last lecture, I have introduced the basic concept of supply voltage scaling, then discussed some approaches based on static voltage scaling. And here is the agenda of today's lecture. After a brief introduction, we shall discuss about pipelining for low power, and then we shall discuss voltage scaling through optimal transistor sizing, and finally, we shall discuss about voltage scaling using high level transformations. As I mentioned, we have discussed voltage scaling approaches, and as you know, there are 4 different categories. We can classify it, you can categorize them in 4 different types: static voltage scaling, multi-level voltage scaling, dynamic voltage and frequency scaling, and adaptive voltage scaling. And in the last lecture, we have discussed about device feature size scaling, and also one of the important approach based on architecture level synthesis, that is parallelism for low power. And today, as I mentioned, we shall be discussing pipelining for low power, and then voltage scaling through optimal transistor sizing, and voltage scaling using high level transformations. Coming to pipelining for low power, first I shall introduce the basic concept of pipelining. What is pipelining? Pipelining is an implementation technique where multiple tasks are performed in an overlapped manner. So, this is the basic idea, or rather how the pipelining is defined. It is an implementation technique. Note at this particular word, implementation technique, and also another important word, overlapped manner. Question is, when can it be implemented? It can be implemented when a task can be divided into 2 or more subtasks which can be performed independently. So, pipelining can be implemented only when a particular task can be divided into a number of subtasks which can be performed independently. So, this is the fundamental requirement for pipelining. For example, here we have got a task which can be performed in time t, let us assume, and if the task can be divided into k subtasks, say we have divided into 1, 2 up to k of equal size, then this can be pipelined, and if they can be performed in an independent manner, then you can implement pipelining. How? Let us see. Different subtasks are performed by different hardware blocks known as stages. So, stage S1 is performing subtask 1, S2 is performing subtask 2. In this way, stage K is performing subtask K, and you can see you are applying clock, and you have got latches in between where intermediate results are stored, and the clock transfers the results from one stage to another in a synchronous manner. So, this is how it is implemented, and the execution is done in this manner. For example, if we consider 5 tasks, task T1, task T2, task T3, task T4 and task T5, you can see task T1 is divided into 4 subtasks which are performed in time tau 1, tau 2, tau 3 and tau 4. And then before the completion of the task T1, you can see after the subtask T1 is completed of task 1, in time in slot tau 2, we are starting the subtask subtask 1 of task 2. So, T21 is the subtask 1 of task 2, and so these two are getting executed in a overlapped manner, because we have got different stages which are able to perform these subtasks. That means, when we reach this time slot tau 4, we find that all the 4 tasks are getting executed in a overlapped manner. However, the fourth part, that means the subtask 4 of task 1 is getting executed in tau 4, subtask 3 of task 2 is getting executed in the same time slot, subtask 2 of task 3 is getting executed in the same time slot, and subtask 1 of task 4 is getting executed in the same way. So, this is how it is getting executed in an overlap manner. I believe before we proceed, let me illustrate with an example, very simple example. For example, say let us consider say undergraduate education, undergraduate education, B.Tech or BE, whatever you call it. Suppose as you know, the undergraduation takes 4 years. So, let us assume that we are admitting students in the year 2010. How long they will take? They will continue up to 4 years. So, 11, 12, 13, 14, 2013. So, one batch will pass out from I mean they will be admitted in 2010 and they will pass out in 2013. Let us assume that we do not have enough resources. So, until the students pass out, we cannot admit a new batch. So, that means another batch will be admitted in the year 2013 as they pass out, and then 14, 15, 16, 17, 2017 another batch will pass out. In this way another batch will be admitted in 2017 and they will continue till 18, 19, 20 and 21. So, we can so 3 batches are passing out starting with 2010 and 3 batches are passing out in 2021. So, every 4 yearly. That means as we admit one batch, we cannot take another batch, and this is how it is going on. In this way we can say this is non-pipelined education. Now, let us say in 2010 we admit first batch, and as they go to second year 2011 we admit another batch, say batch 1, then batch 2 we admit in 2011. So, first batch is in 2011, second batch in the first year, first batch is in the second year of second year and the second batch is in first year. So, then batch 3 will be admitted in 2012 and batch 4 will be admitted in 2013. Then 2013 and 2013 sorry, this is the batch of 12, 13, 13, 13. And so, here in the year as we go to year 2014, we find that batch 1 will pass out, batch 2 will go to fourth year, batch 3 will go to third year and batch 4 will go to second year, and batch 5 will go to first year. So, you can see if we consider the year 2013, we can see batch 1 is in the fourth year, batch 2 is in the third year, batch 3 in the second year, batch 4 in the first year. So, this is nothing but pipeline implementation of the education. This is a very simple example of pipelining, and this kind of example we will find in our day to day life in many places, everywhere, in automobile industry and many other places you will find this, how it is being done. So, only requirement for this pipeline implementation, this we can say as pipeline implementation. Obviously, you will require more hardware resources. So, more hardware resources, because you will require more classroom, more laboratories, more hostels and so on to accommodate students of 4 batches. But the advantage is every year one batch will pass out. 2003, 2004, 2005. That means after the initial entry, all the students will, I mean every year one batch will pass out. That means here throughput is one batch per year. Earlier it was one batch per 4 year, and here one batch per year. So, throughput is 4 times by using pipelining. So, this is a very simple example of pipelining, and exactly what I have shown here. In the same way, the pipeline education is taking place. Okay. Now, in the context of pipelining, there are some performance parameter we use. Number one is clock period. Clock period is, as you have seen, when we go for implementation, we have to use some latches we have seen here, and we have to apply a clock. So, what is the clock frequency? So, clock frequency is decided by the maximum time delay of the stage plus other delays due to latches and other things. So, it will be slightly more than the time required to perform a subtask in a particular stage, and frequency will be decided by this maximum delay, that is 1 by tau is the clock frequency. And you can see we can measure the speed up for a k stage pipeline. Say whenever you are performing n tasks, you will require how much time will require in a non-pipelined manner. In a non-pipelined manner, you will require n k tau. On the other hand, you will require k plus n minus 1 into tau. I mean non-pipelined manner the time required is non-pipelined time required is to execute n tasks is n into k into tau. This is the time required for each task, I mean k into tau, and for n task it will require n k tau. On the other hand, for pipeline implementation, we have seen that after the k minus 1 stage, you will require only k minus 1 plus n. So, first batch will come out here and nth one will come out here. So, this into tau will be the time required for non-pipelined one. So, speed up that you achieve by using pipeline is n k tau by k minus 1 plus n into tau. Tau will cancel out. So, this is equal to n k by n plus k minus 1. Now, when n is very large, say it is infinity, that means you have to execute a very large number of tasks. In such a case, what will happen? You can ignore this will this will become n k by this one can be ignored. So, this will become equal to, this will approach. So, for a large value of n, what will happen? This will become equal to k, n into k and n plus k. That means, this part will become equal to k. That means, speed up will be a factor of will be equal to k. When n is large, you can make it, it will become equal to k. So, we find that speed up can be, that means the ideal speed up can be k, where k is the number of stages, and efficiency is essentially the ratio of the actual speed up to the ideal speed up, and ideal value will be equal to 1, because S k, as we have seen, ideal value is k. So, S k by k will be equal to 1. On the other hand, throughput, that is the number of tasks that can be completed per unit time, will be equal to W equal to eta by tau, and that will be equal to again it will be equal to f. That means, f 1 by tau, that is equal to epsilon will be equal to 1, and so it will be 1 by tau. So, number of tasks that can be completed per unit time will be f, because per cycle one task can be will be completed in a pipeline system. So, this is the fundamental principle of pipelining, and pipelining is widely used not only in our day to day life in many situations, but it is used in computers. So, inside computer the pipelining in all modern processors pipelining is used, particularly to implement execution of instructions. But primarily what is being done in modern processor, pipelining is used to improve performance, to have speed up, to have higher throughput, and we have seen how the throughput is increased, how the speed up is achieved. But what we shall discuss is how pipelining can be used to achieve lower power, not pipelining for performance, but pipelining for low power. Let us see how it can be done. Let us go back to our original example, that means performing 16-bit addition, and here is the pipeline implementation of 16-bit addition. We have done it by using 2 stages. So, we have got 2 stages, each stage is of 8-bit. That means, the 16-bit addition has been divided into 2 8-bit additions. So, here the 16-bit addition is a task which has been divided into 2 subtasks, each of 8-bit addition. So, you will require 2 8-bit adders in each stage, and you can see in this stage, in a particular stage we have got 1 8-bit adder and another 8-bit adder in the next stage, and intermediate results are stored in these latches. You can see that this value, that S0 to 7 will be stored here, and this carry will pass on to the next stage, and that will be added in the next clock period. And you can see here finally you get S0 to 15, sum you are getting and carry you are getting from this particular second stage. So, in this implementation, as you can see, we are performing 8-bit addition instead of 16-bit additions. So, therefore, the time required will be half that of 16-bit addition. That means, the delay of the 16-bit adder is double that of the delay of the 8-bit adder. So, what we can do, if we want to perform the computation during the same period, that means, the time required to compute 16-bit addition, if we want to perform 8-bit addition in the same time, then what you can do, you can reduce the supply voltage to half. So, it will perform 8-bit addition in the same time, and that is what is being done here. So, we apply a supply voltage V reference by 2 to this adder as well as to this adder. Of course, the clock frequency will be F reference, because the throughput we are not compromising on throughput. It will keep on producing result at every clock cycle of F reference. So, using this implementation, what kind of performance we achieve? We can see the or what is the power dissipation. So, power dissipation P pipe will be equal to C pipe, that is the capacitance of this circuit, this part of the circuit, and here you can see this is an 8-bit adder, this is an 8-bit adder. So, these two together makes 16-bit adder. Only additional things are latches. So, the increase in capacitance will not be as high as the parallel implementation. We have seen in parallel implementation using 2 parallel adders, the increase in capacitance was 2.2 C reference, but here it will be much less, and that is the reason why it is 1.15 C reference, 15% increase in capacitance because of the latches. However, you will be applying a supply voltage of V reference by 2. So, the power dissipation is 1.15 C reference into V reference by 2 square, and however, this will be F reference, this reference is missing, but this is the F reference. So, this value if you compute, you will get 0.28 P reference. That means, the power dissipation is 28% of the that original 16-bit addition. So, we find that we are able to reduce the power dissipation by voltage scaling. However, we are maintaining the throughput same. That means, this is essentially pipelining for low power and not pipelining for performance. So, here we have compared these two situations. Whenever we do pipelining for performance, in such a situation there is an increase in area by 15%, there is an increase in power dissipation by I mean 2.3x, that means 2.3 times of the original adder, but we get a throughput of 2x, that is 2 times. So, instead of that, here if we are doing pipelining for low power, we find that there is an increase in area, that means we are trading area for lower power. So, lower power is 0.28x and throughput is remaining same. So, this is the this is how you can achieve pipelining for low power without compromising performance, but you will require a little more area, as we have seen. Now, we can combine pipelining with parallelism. So, earlier we have discussed parallel implementation, and today we have discussed pipeline implementation. We can combine parallelism with pipelining. That means, we can have two parallel implementation and each of them is pipelined. So, here you can see we have got a 16-bit adder implemented in pipelined way, another 16-bit adder, pipelined 16-bit adder. So, we have got two 16-bit adders, each of them is pipelined, and in such a case obviously you will require two 8-bit adders in the first stage and two 8-bit adders in the second stage, and you will require a multiplexer as you require in case of parallel implementation to take the output here. And these adders will be operating at a lower voltage, much lower voltage, even less than V reference by 2, and the clock frequency here is F reference by 2. Here the clock frequency will be F reference by 2, because here you are generating at half the rate, and the output of the multiplexer you will be getting at the full rate. So, throughput here will be same as the original circuit. However, this part of the circuit will be operating at a lower voltage and with a lesser speed, because clock the rate at which data will be inputted will be F reference by 2. Now, let us see what is the estimated power. So, this parallel, so pair pipe, P pair pipe, that means parallel pipeline implementation, the capacitance is increasing by a factor of 2.5, supply voltage is 30% of the original circuit, and frequency is F reference by 2. So, if we multiply, we get 0.1125 P reference. So, we find that the power dissipation is roughly equal to 11% of the original circuit. That means, if we go for parallel and if we combine parallelism with pipelining, we get still, I mean, larger reduction in the power dissipation, and of course, in this case we are maintaining the same performance. So, here you can see the comparison in the this particular column gives you whenever we do not do voltage scaling. So, without voltage scaling, that means we get higher throughput at the cost of larger area and larger power dissipation. So, with an increase in area of 2.5x and power dissipation of 2.5x, we get a throughput of 4x, because in this particular case it is possible to have 4 times throughput compared to our original 16-bit addition. But instead of that, if we go for parallelism and combine parallelism and pipelining for low power, and we do voltage scaling, in such a case we can see although the area increases by 2.5 times, the power dissipation is 0.1125 times of the original circuit, keeping the throughput same as the original one. So, this is how we can use parallelism, we can use pipelining, we can combine parallelism with pipelining to achieve lower power. Okay. Now, we change gear and shift to another topic, voltage scaling through optimal transistor sizing. What do you really mean by transistor sizing? We know that a transistor can be realized with different length and width. So, whenever we increase the width, what happens? The resistance decreases. That means, if the width of a transistor is increased, the resistance reduces. So, one very common technique to reduce delay is transistor sizing. That means, suppose this particular stage, one inverter stage is driving a large capacitor. Earlier we have discussed in detail how we can drive a large capacitor. We have seen that you can use inverters with a higher W by L. That means, W by L ratio is increased, and instead of single stage, multiple stages can be used to achieve smaller delay. So, sizing, transistor sizing is very common in reducing the delay. Now, instead of reducing delay, if we are interested in lowering power dissipation, can we use transistor sizing? So, I shall explain how it can be done. So, voltage scaling through optimal transistor sizing. So, here we have done some experimentation. You can see as the fan out increases, fan out means you can see, say suppose you have got an inverter. If it is driving only one inverter, the fan out is 1, fan out is equal to 1. If it is driving say another gate, then fan out is 2. So, as the fan out increases, as you know, the output capacitance increases, because the gate capacitance of the next stage is coming, and also parasitic capacitances are there for interconnection. So, that means, as the number of stages as the fan out is increasing, the delay increases. Now, you can do the sizing of this transistor such that this delay is reduced. Question is, what is the optimal sizing? How much I mean the width has to be increased by what ratio? So, that you can find out from this particular curve. You can see this particular curve corresponds to fan out is equal to 3. Then when fan out is equal to 4, you can see delay is larger, but reduction is more as we go for further increase in fan out, and the lower curve corresponds to fan out 4. We can see the delay is reduced more whenever the fan out is more. That means, the sizing has more impact, is more effective whenever the fan out is more. On the other hand, fan out is less, the reduction in delay is less. As you can see, if we consider say sizing factor 2.5. So, in the first case, when the fan out is equal to 3, there is a small reduction. So, here it is reduced from 1 to, it is normalized delay. So, it is reduced to 0.85. On the other hand, if we consider this curve, so with fan out is equal to 8, you can see it is reduced to 0.55. That means, the reduction is more. So, what can be done? Let us consider one particular curve, say for a particular fan out. This is the curve. Now, what can be done? We can draw a tangent, that means, this particular line that corresponds to delta delay by delta sizing factor size, which is equal to -1. We find out this particular point where it is -1, and this is the optimum sizing factor. So, this sizing factor is considered to be 1, because up to this point it reduces and reduces more sharply, and after that reduction is not much. As you can see, it more or less saturates. So, the delta D by delta S points we find out depending on the fan out, and the transistors can be sized by that ratio. So, then we follow these steps. So, we have a complex circuit where there are some critical path and non critical path. So, upsize gets on the critical path to reduce delay of the circuit. Obviously, as we increase the do the sizing for on gates of the critical path, there will be reduction in the delay. And then second step is scale down the supply voltage to equalize the original delay. That means, whatever the reduction in delay occurs there, now we are scaling down the supply voltage such that whatever delay we achieved, we use that slack, and as a consequence after this time the delay will be equal to the original circuit. However, the supply voltage will be less, and as a consequence there will be significant reduction in the power dissipation. However, whenever you reduce the supply voltage, many non critical paths will become critical. So, again you have to selectively identify transistors in the non critical path, and then introduce sizing in a selective way, so that the delay is not more than the critical path. This is how by using these 3 steps we can do voltage scaling by optimal sizing of the transistors. So, what essentially we are doing, normally in a complex circuit, if we plot the delay distribution, delay distribution will be here. This is the delay distribution. Delay is on this line, and here number of paths in the circuit. You will find that it will have a plot like this, kind of Gaussian distribution. That means, the number of paths is large in the middle and the delay is more. This is the critical path delay. This is the critical path delay, and there are many other paths which will have smaller and smaller delay, and delay will vary over a range. So, this is the normal distribution of delays on different paths in a complex circuit. Now, what we are doing initially, we are increasing the size. By sizing, we are reducing the delay and pushing it maybe to this point. Then we are increasing the. So, this is the first stage, reduction in delay in first stage, in step 1. Then what we are doing, whatever slack we achieved, we are reducing the supply voltage, and as a consequence delay is increasing again, and it becomes same as the original. So, this is the step 2. Step 2 by supply voltage scaling. Supply voltage scaling. So, after that what will happen, as we do the supply voltage scaling, some of the delays of the non critical path will go to this side and may exceed this path. In such a case, again you have to do sizing, so that all the delay for all the paths remains within this critical path. What does it mean? As the delay is remaining within the critical path, there is no loss in performance. That means, performance is not compromised, but because of larger supply voltage we are achieving in the second step, there will be significant reduction in power dissipation. So, this is the technique in which we have done voltage scaling through optimal transistor sizing. So, this is how you can utilize sizing. Obviously, whenever we do this, there will be increase in area, because wherever we are upsizing, there will be increase in area. That means, here again we are trading area for lower power by this technique. Okay. So, this is the second technique that we can do. Now, let us focus on third technique. voltage scaling using high level transformation. Whenever we are realizing some circuit, we can do high level transformation. What kind of transformation we shall do? Let me explain with the help of this example. Suppose we have to realize a first order IIR filter, infinite impulse response filter. As you know, the expression for that filter is y n is equal to x n plus k into y n minus 1. So, this is how repeatedly this is computed in a iterative manner. You can realize the circuit in this way. You will apply x n, this is the input, x n will be added with y n minus 1, and you will have to multiply with a factor, you have to multiply with k. And how do you generate this is where you will generate y n, and y n minus can be generated by a delay element or latch. So, this is where you will apply clock. So, this is how the circuit can be realized with the help of an adder and a multiplier. So, this computation will go on as you apply different values of x n, and k is a constant that is fed here, and this is how you can realize a IIR filter. And the corresponding DAG is shown here. Here is the corresponding DAG, that means you are doing multiplication in one step in one times one clock cycle, and addition you are doing in the next clock cycles. That means this is the directed acyclic graph, and you have done the scheduling. You know, whenever you do high level synthesis, you have to do the scheduling. So, scheduling is done in this way, add the multiplication in the first time slot and addition in the second time slot. So, this is how you can do the computation. So, this we shall use as reference. So, let us assume the supply voltage is 5 volt and throughput is 1 x, and power that is required for this computation is 1 x. Now, let us go to some kind of transformation. What we have done in this particular case, we are computing two outputs simultaneously, and by using a technique known as loop unrolling. So, the loop unrolling is a very useful technique that is used in many situations. For example, whenever we go for optimizing compiler, that compiler does loop unrolling to improve instruction level parallelism, which helps in having more instructions which can be executed in parallel. That is important in the context of minimizing hazards in pipeline circuits. So, that is done in optimizing compiler. Here also we have done loop unrolling. So, loop unrolling means what is being performed in one iteration, we are performing in a single iteration, we are performing two such operations. We can unroll it 3 times, then what is performed in 3 iterations, now it is done in single iteration. So, what happens whenever we do loop unrolling, the size of the code increases, but in this particular case we are not doing by executing instructions, but using hardware. So, here if we want to generate y n minus 1 and y n together, obviously we have to duplicate the hardware, and this is the corresponding DAG. So, here you will be applying y n minus 2, k, x n minus 1, k and x n, and here you will be generating y n minus 1 and y n together. So, you can see two outputs are generated simultaneously. Now, you may be asking, is there any benefit by doing this? You are requiring 4 clock cycles and you are producing 2 outputs. Earlier you were requiring 2 clock cycles, you are producing 1 output. So, there is no benefit. So, simply by doing loop unrolling, it does not give you much benefit unless you exploit some features of loop unrolling. What can be done? You can do some transformation. So, here what we are doing, we are using kind of constant using technique like constant propagation and using the property of distributivity, and by doing that you can see the computation can be done in 3 steps in 3 clock cycles. So, here we are computing k square and keeping it in a resistor that is available as a constant. So, you can see y n minus 1 is produced in this way. Here you require y n minus 1 is equal to x n minus 1 plus k star y n minus 2. So, this requires 2 clock cycles. So, this multiplication is done here k into y n minus 1, and then addition with x n minus 1 is done here. So, you get here y n minus 1. Then in this to produce y n, we are doing some kind of simplification. We are substituting y n minus in this expression, and then we are getting this expression x n plus k star into x n minus 1 plus k star y n minus 2. So, here y n minus 1 has been substituted, then we are simplifying it to get this expression. So, x n plus k into x n minus 1 plus k square into y n minus 2. So, this is being implemented in this part of the circuit. So, this obviously will require 3 clock cycles. So, you can see here whenever you do this kind of simplification, this kind of transformation, we can compute in 3 clock cycles. Now, we have got 2 options. We can compute in 3 clock cycles, and obviously, we are able to compute faster than the original circuit where you have done loop unrolling. So, here it requires 4 clock cycles, here it requires 3 clock cycles. Instead of that, what can be done? The time required for 3 clock cycles can be made same as that of time required for 4 clock cycles by reducing the, how can it be done? By reducing the frequency and simultaneously reducing the supply voltage. So, we reduce the supply voltage because we are increasing the slack, whatever was required in 3 clock cycles, now we are doing it in 4 clock cycles. So, we can afford to use lower supply voltage, and that is what is being done in this particular case. So, you can see we have done supply voltage scaling. The voltage of the for this implementation is reduced to 3.7 volt, and throughput is 1x and power dissipation is 0.6x. So, you can see there is a significant reduction in power dissipation. Of course, we could have, as I mentioned earlier, these techniques can be used to improve performance as well. So, if we do not do supply voltage scaling, if we operate at 5 volt, then throughput increases by 33%, because we are completing our execution in 3 clock cycles instead of 4 clock cycles. However, at the cost of higher power dissipation, larger power dissipations. That means, we are dissipating 1.5 times that of the original circuits. I mean, of course, spark computation. So, you require 3 multiplier, 3 adder. So, in the original circuits, but you are producing 2 outputs. In the original circuit, it was 1 multiplier and 1 adder to produce 1 output, but here you are producing 2 output, and it is 3 times. So, hard power dissipation will be 1.5 times that of the original circuit. So, you see here also we can do transformation and then supply voltage scaling to achieve lower power. We can still reduce power dissipation by using a technique, by using pipelining. So, this particular stage can be pipelined. How can it be pipelined? You can see in the stage 1 we shall compute Z, some intermediate result, then Z will be used in the second stage to produce the y n minus 1 and y n. So, the implementation will be somewhat like this. Say you will be applying x n, k k x n minus 1, these 3 will go to a latch, these will go to a latch, this is the first stage latch, and then you will be requiring a multiplier. So, k into x n minus 1, this x n minus 1 and let it be k. So, x n minus 1 and k, these two are applied here, and then we do addition. So, this output is coming here and this produces z. Now, you will require another stage, and there you will be requiring multiplier, adder, multiplier, adder. So, what we will be applying here? Here you will apply multiplication k, this factor will go there, k, and you are multiplying it with x n minus 1, x n minus 1. So, x n minus 1, k into x n minus 1, and you are adding with, this will be, this is y n minus 2, this is y n minus 2, y n minus 2, and here it will be x n minus 1. And in this particular case, you will be applying again y n minus 2 and k square, and here from this stage will go addition will go z, this z is going there. Obviously, all those other inputs will pass through the first stage, and here it will produce at the output of this you will get two outputs, one is your y n minus 1 and y n. So, this is the pipeline implementation, and here you will apply clock. So, you can see here each of these stage will require 2 clock cycles, because you have got 2 stages. So, this stage will require 2 clock cycles, that means delay for each stage is equivalent to 2 clock cycles. That means, after the pipeline is filled up, it will produce output at the interval of per 2 clock cycle of the original circuit. That means, the clock frequency is twice that of the original circuit. That means, in this case if you look at this particular diagram, we find that in 2 time slots all the computation can be done. So, the first stage will require 2 clock cycles, the second stage also will require 2 clock cycles, though the clock frequency of the pipeline stage is decided by 2 clock cycles. That means, you have got two option again here, either you can do the computation and produce result quickly, or you can reduce power dissipation by scaling down the supply voltage. So, here is the result for that. Whenever you do voltage scaling and the time required, time to produce these outputs will be same as that is required in this circuit. So, whatever time is required, 4 clock cycles, same time is required here. In that case, throughput is remaining same, that means the rate at which outputs are generated is identical. However, there is a significant reduction in power dissipation, 50%. On the other hand, if you want to speed up, have higher throughput 2x, then of course, it can be done by using higher power dissipation, by larger power dissipation. So, this is achieved by using loop unrolling and pipelining. So, you can see we can do transformation, high level transformation, and also you can make use of pipelining to reduce power dissipation. Now, the question arises, how many stages you will use in this pipeline stage. So, here is the curve for different situations. As you can see, the unrolling factor can be increased. We have considered where the IIR filter operations has been unrolled by 2 times. you can unroll it by 3 times, 4 times, 5 times and so on. So, what is the benefit that we achieve by unrolling by more number of times is shown in this particular diagram. First of all, if we let us focus on the power dissipation, we can see whenever we do 2 times, there is significant reduction in power dissipation. We have seen 50% reduction in power dissipation, keeping the throughput same. If we unroll by 3 times, still there is reductions, it comes to about, that means 9 instead of 25. So, there is significant reduction, but further increase in unrolling does not really reduce the power dissipation, because overhead increases. So, overhead itself the benefits of more unrolling. So, up to unrolling by a factor of 3 gives you benefit. However, as you do the unrolling, you can see here other parameters like capacitance. Capacitance keeps on increasing as it is shown by this, linearly it increases, because number of additional, as you do the unrolling, they will be requiring more and more hardware, and so the capacitance will keep on increasing. Speed up factor will increase, speed up will also increase linearly, but voltage that you can use can be reduced only initially as you go from single stage to, I mean, to unroll by 2 or unroll by 3. Beyond that, it does, you cannot really reduce the supply voltage much, and that is the reason why we were not getting reduction in power dissipation. That means, there is a optimum unrolling factor, beyond which it becomes a point of diminishing return, and at some point there is no return at all. So, that means, you have to choose a unrolling factor which gives you maximal benefit, and beyond that it does not give you much result. So, with this we conclude our discussion on this topic. Now, we can summarize what we have discussed so far. We have discussed device feature size scaling in the previous lecture, and we have seen how it has helped to reduce supply voltage with improvement in performance. And we have discussed several architectural level approaches like parallelism, pipelining, and we have also discussed multi-core implementation and how they can be used to achieve lower power by exploiting parallelism. And also we have discussed voltage scaling using high level transformation that can be used to realize lower power, and also we have discussed how sizing can be done to reduce power. So, with this we have come to the end of today's lecture. In the next lecture we shall discuss about other techniques like multi-level voltage scaling. Thank you.